Okay, so previously we learned how to construct a confidence interval about the population mean, but we needed to be careful and make sure that two things occurred. One was that we knew what the standard deviation for the population was, and the other was that we had a sample size of 30, n equals 30 or greater. But that's not always the case, and that's actually typically not the case. So typically we certainly don't know what the standard deviation is for the population. So what we've done is we've come up with a way to use a different distribution, the t distribution, to solve these sorts of problems. So the two big issues that we have here so when the shape of our x-bar distribution, or our sample distribution, our sample mean distribution, is not always known. So if sigma is also not known, then we can't calculate our sigma of this equals sigma over square root of n, sigma of our sample distribution, sample mean distribution, because we don't know what sigma is. So what we're going to do is we're going to use a new distribution to account for these situations, and that distribution is our t distribution. So the t distribution is really not one distribution, but it's a family of curves. A family of normal curves. So if we use for a reference a standard normal curve, say this is our standard normal curve. Here, the mean equals 0, and sigma equals 1. Well, we might have a t curve that looks something like this, a little more spread out, maybe a lower peak, but still a normal curve. This is one of our t distributions. And another t distribution might look like this, might come in a little higher. But they're still normal curves, bell-shaped, mound-shaped curves. But the difference between these is they're more spread out, so their standard deviations are different. And the way we differentiate between these curves is a new idea we call degrees of freedom. Talk about that in a second. But for example, the degrees of freedom of this red curve might be 200, whereas the degrees of freedom, I'm just going to put DOF, of this green curve might be 50. So as the degrees of freedom get higher and higher and higher, which is associated with more and more data points, then as we go to infinity, the t curves actually match up with the z curves. So t approaches z as n, the number in our sample set, goes to infinity or gets bigger. So what is this degrees of freedom we're talking about here? So degrees of freedom. Well, the degrees of freedom are the number of independent values that can vary in an analysis without breaking constraints. Well, that doesn't seem to necessarily make things any more clear to you, probably. So let's look at a basic idea here. Suppose I have a random sample and I have 10 values in this random sample. So I have 6, I have 8, I have 5, I have 9, I have 6, I have 8, 4, 11, 7, and then I have a value which we don't know, which I'm going to call x. And when I sum all these up, because I know what the mean is, I sum all these up. Let's say that I know that the mean of this sample is 6.9. So if I were to sum all these up, then they would need to equal 69 here, because I have 10 of them. So 69 divided by 10 equals 6.9. So I know this value of 69. I know these 9 values, but what I don't know is this value. But this value is dependent on all these other values. So x must be x equal to 5. Well, we can say then that 9 values vary. So these 9 can vary any way possible. But 1 is dependent on all those values, how they vary, in order to get to the 69. So we have a situation n minus 1 equals 10 minus 9 equals 1. This is what we call 1 degree of freedom. And this is going to always be the case with everything we're doing in this class. Our random samples will always have 1 degree of freedom. So you'll never have to really put in a lot of effort to calculate that. You just always know that the degrees of freedom are n minus 1. That's important because we need to know this value in order to decide which t-curve we're going to use. Because as you recall up here, with our t-curves change, although they're normal shaped. The exact size of these t-curves and shape of these t-curves change based on the degrees of freedom. And of course, if n goes to infinity, then this t-curve will completely superimpose exactly on top of the standard normal curve. It approaches the standard normal curve as n goes to infinity. So using this t-curve now, we can construct a confidence interval around our mean. And so we're going to have a new equation now. So we're going to have the sample mean minus, instead of z though, it's going to be t alpha over 2, but it's going to act in the same way. It's just going to be a different number. S over square root of n is less than mu is less than x bar plus t alpha, sub alpha over 2 s over square root of n. And in this relationship here, x is the same as it was before, x bar is the same as it was before. It's our sample mean. N is the same as before. It's our sample size, just like it was before. But now we have some new terms. We have S here is our sample instead of the population. It's our sample standard deviation. And T we get from the T-curves based on this alpha. We'll see that. And of course over here, mu is still our population mean. It's what we want to try to figure out, get some idea of. Okay? So, to demonstrate this, let's just go into an example. The actual practice of this is a little easier than explaining it. For example, let's say you have a sample of 22 data points, random data points, n equals 22. Maybe it's 22 feet shoe sizes, maybe it's 22 heights, maybe it's 22 days temperature, maximum temperature or something. But it's 22 pieces of data. And we want to construct a 95% confidence interval for the population mean. So this is the same thing we've done before. But in this case, we don't know what the standard deviation is. So we're going to have to resort to using t. Well, the first thing we need to do is, well, draw a picture. What's going on here? So 95% confidence interval means that alpha equals 1 minus 0.95 equals 0.5. So if this area is 95%, then these two shaded areas equal alpha. And any one particular shaded area is alpha over 2, or 0.5 divided by 2 equals, this is, oh, bother. This is actually 0.05. It's 5% is left over. So it's 0.05. This is 0.052 also. You probably noticed that and we're screaming at the screen. So this will be 0.025, which is half of that. So we need to find t alpha over 2, or t of 0.025. And I'm going to stop this video and pick up in the next video and show you how to do that.